Okay, let's take a look at homework number 7 after our disastrous internet experience. Um, 4 questions. There's a graduate question as well. I just wrote up some little hints, and we've gone through this before verbally for the undergraduate questions. Number 27.1 says, pick yourself an analytic function, f of z equals u of r theta plus iv of r theta, and show that the real and imaginary parts satisfy this thing here. This is Laplace's equation in polar coordinates. Okay, well, if we've got an analytic function, you know it satisfies Cauchy-Riemann equations. By the way, these are the 2 Cauchy-Riemann equations in polar coordinates. There was something on the first test that involved that. So we know this. Oh, and in fact, if we've got an analytic function, we know those partials, derivatives, everything's continuous. So we've got continuity. In particular, if we see any mixed partial derivatives, that continuity will let us draw a conclusion about equality of mixed partials. And you're going to see mixed partials. All right. So we know the real and imaginary parts satisfy the Cauchy-Riemann equations in polar coordinates. So here's my big hint for you. Take this equation from Cauchy-Riemann, take a partial with respect to r of both sides. Take the other one, take a partial with respect to theta of both sides. Now what's going to happen is, here you're going to need a product rule, because we've got a function of r itself, and we got a function of r, the partial of u with respect to r, of r and theta. Well, that's a function of r and theta as well. So what we'll get is a product rule on this side, partial with respect to r on this side, will give us v sub theta r, that is the partial of v with respect to theta, and then with respect to r. On this side, a similar thing, partial with respect to theta, gives us second partials with respect to theta here. Don't need a product rule over here. R, or negative r, is constant with respect to theta, treated as a constant. V sub r, partial of v with respect to r, is a function of r and theta. So we'll need to differentiate this, and we'll pick up a v sub r theta, a partial of v with respect to r and then theta. So on this side, you've got a mixed partial v sub theta r. On this side, you've got a partial v sub r theta. But wait, those are equal because of the continuity that follows from knowing f is analytic. So continuity of partial derivatives, v sub r theta equals v sub theta r. And that little piece of information right there lets you glue these two together. So you'll glue these two together, you'll ultimately eliminate the v function, and you'll have a relationship between u sub r, u sub r, u sub theta theta, and some other stuff. And it'll turn out to be exactly this right here. Plug into the left-hand side and it will produce the right-hand side. The second question, number 9, 115.1, this comes out of so deep in the book because the 8th edition of the book has things in a slightly different order than the 9th edition. So in the 9th edition it had jumped to, I don't know, section 115. But we're really still covering material from the harmonic functions section, harmonic conjugates. You're given a function u, and you're asked to show that that function is harmonic and to find a harmonic conjugate. Okay? Piece of cake to show this is harmonic. Take second partials with respect to x and y, add them together, you'll get 0 because it is harmonic. Now, if we're looking for a harmonic conjugate, if we can find a harmonic conjugate, v of u, then u and v will have to satisfy the Cauchy-Riemann equations. So that tells us that when we got the u function, we can find the partial of u with respect to x, just differentiate that. That must equal the partial of v with respect to y, and v is the function we're looking for. Okay, so let's take a partial with respect to x, that'd be 2 minus 3x squared plus 6xy, 2 minus 3x squared plus 6xy. Oops. Partial with respect to x, plus 3y squared. So let's see, partial with respect to x, 2 3x squared with respect to x would leave us plus 3y squared. And we're requiring that to be, by the Cauchy-Riemann equations, the partial of v with respect to y. Boy, well then let's just take this and anti-differentiate it with respect to y. That'll give us, within a constant of integration, the v function. So integrating with respect to y, 2 becomes 2y. Negative 3y squared becomes negative 3x squared, partial negative 3x squared, anti-differentiate with respect to y, becomes 3x squared y. This is the interesting one, 3y squared, anti-differentiate with respect to y, it's just y cubed. And well, we need to add a constant. Now we're taking partial antiderivatives. You did that in Calculus 3 when you dealt with integrals of more than one, functions of more than one variable. Let's check it. If this is right, I should be able to differentiate both sides with respect to y and get the previous line. Partial of v with respect to y, v sub y. Derivative with respect to y would be 2, would be negative 3x squared, would be 3y squared, and yeah, it would be 0, so that's gone. So we need something that's constant with respect to y, and that could depend on x. So we get this unknown function. This is exactly like one of the examples in the book. So we still haven't found v, but we found the form of v. We also ain't used all the information we have from the Cauchy-Riemann equations. We also know that the partial of u with respect to y, well, we got u right up here, that we can compute, must equal the negative partial of v with respect to x. Well, we got the form of v right here, so we could take a partial of this with respect to x, substitute it into this piece of the Cauchy-Riemann equations in rectangular coordinates. I've written some of it at the bottom. That sets up a relationship that allows us to find phi of x. Actually, it first allows us to find phi prime of x, from which we'll find phi of x with ordinary antiderivatives at that stage. And once you've found phi of x, then we can plug back in here, and you found that harmonic conjugate. So, in a sense, this is pretty easy. It's just there's a bunch of antiderivatives and differentiation. Are you good at antiderivatives? Well, this kind of stuff you're good at. It's just powers of x and y. Over here, let's look at, it's obscure, there we go, let's draw like this. Number 29 says, use theorem 2.27.a to prove that if f is analytic and not constant throughout a domain, D, then it cannot be constant throughout any neighborhood lying in D. All right, so they've given you not constants, and there's a bunch of negations in there. So to peel the logic apart, I recommend the following. Let's go for proof by contradiction. They said we don't have a constant function f when that function is constant on some little neighborhood. Let's denote that little neighborhood as capital N. And suppose the function f of z equals some constant, call it w sub 0, throughout some little neighborhood, that is a little open connected set, that is in the domain capital D. The purpose of this one is uniqueness of analytic functions. Theorem 27.a tells you that a function that is analytic on a domain D, its behavior is determined by its values on an open neighborhood, like we have here, or a line segment. We've got an open neighborhood, so it contains lots of line segments. But anyhow, it's the open neighborhood piece of it that we're applying here. And I know that, hey, if the function is constant on that little open neighborhood, this theorem tells you it must be constant everywhere. But that contradicts the hypotheses here that say it was given to be not constant. So assume we have this kind of behavior on the neighborhood. That implies a constant function. Contradiction. It can't have this kind of behavior on the neighborhood. So that's how you piece together all the negatives, the negations that they've given throughout. And the last one, this one's which is the easiest one of the four probably, says, consider f of x plus iy equals e to the x cosine y plus I e to the x sine y. You recognize that guy? That's just the exponential function written in terms of x's and y's. Factor the e to the x out, use Euler's formula. That's what we've ultimately defined to be the exponential function. And they want you to show in two different ways that this function satisfies the equation f of z conjugate equals f of z conjugate. They want you to do it two ways. They want you to do it using the reflection principle. Okay. Reflection principle said if such a function has a domain that's symmetric with respect to the real axis, and the domain of this is everything. It's an entire function, in fact. So domain is a whole complex plane. I don't have to worry about that symmetry stuff. And if, when I plug a real number into this function, we get a real number out, then the reflection principle holds. What did the reflection principle state? It was this little equation right here. So all we got to do is plug in a real number to the function and see if you get a real number out. Let's plug in x, if you like, x plus I times 0. We'll take y to be 0. Follow your nose. This will be 0, sine of 0 is 0, cosine of 0 is 1. You'll be left with an e to the x function, and that's real. X is real, e to the x is real. So real inputs yield real outputs. Reflection principle tells you this holds. And they wanted you to do it directly. Okay, so we'll just take, let's take f of z conjugate. All right, here's f of z. So we'll take a conjugate of this. What happens when you conjugate that? There's the only little imaginary part right there. So we'll get a negative in front of that. And we'll take f of z conjugate. That would be f of x plus iy conjugate. That would be f of x minus iy. Now, all right, well, you're effectively just going to replace y with negative y in the definition of the function. See what you get out of that. They'll be the same. So there's the hints on homework 7. Let me get that from you Thursday, and I'll be sending you a link about where to find this video. I'll hopefully see you kids Thursday.